All right. Hello, everybody. It's a great pleasure to speak to you about incremental static analysis. We are Tamás Sáhol and Sebastian Hedwig. We're both affiliated to Delft, which is where we do research, and Tamás is also working at a company in Germany called IDEs. So if you're here, then you probably know that software failures are all around us. So for example, researchers have estimated that in 2016 alone, the cost of software failures was somewhere between gross domestic product of Mexico and Spain. Right? So we're talking about a massive amount of losses here. And so let's take one particular example, which is the heartbeat bug in OpenSSL. Let's see how maybe program analysis could have helped prevent this bug. And then let's discuss about why that didn't happen. All right, so this is a simplified version, obviously. So what happens is we have this heartbeat request coming in. The heartbeat request has a certain length and a certain payload. And the idea is that the server will just echo back the message to the client. All right? So the problem is that the client can actually lie about the length of the payload. So we can say, OK, our payload length is 17, but then we actually only send 3 bytes. Okay? That's problematic. And you would expect the server to detect that, but it doesn't, or it didn't. So what's happening is we allocate a buffer for the size of the message that we want to echo back. We do some administrative management in the S2N function, and then finally we do mem copy. Right? And that's where the problem occurs. So what we're trying to do is we're trying to copy the entire payload, and we're trying to copy payload length many bytes from the payload into that new buffer. And that's problematic, right? Our payload only has 3 values, and we try to read 17 values, so we read far beyond the buffer, and we just read from memory and send it right away. Not so good. So what we've seen here is we've seen source code that has some failure in it. Okay? And well, what we typically do with source code is we compile it. So why didn't the compiler find this? Well, compilers only do very simple static analyses, and the kind of data flow analysis that would have been required to detect the heartbeat bug is not typically done by compilers. So the failure persists into the binary. But that's okay, we do testing, right? So before we deploy, we test the code, obviously. But, well, testing is not exhaustive. And again, this particular error was not found for a long time, and so people could exploit that. So what we would like to do is we would like to make sure that these kind of failures cannot occur in production code. And the technique that we're going to talk about today for doing this is program analysis. Program analysis produces automated feedback given the source code. So it reads in the source code and computes feedback about that source code. And that allows developers to improve the source code and, well, by predicting failures before they happen. So let's go back to the heartbeat bug. One thing we could have done here was advanced analysis. So we could try to figure out what is the size of the buffers that we read from, that we write to, and are they big enough for the memcopy operation down here. So let's say the length of the incoming request is m, then the length of the payload is m-2 to m, so this is an interval. We don't know exactly how big it is, and that's because this n to s function sometimes removes 2 bytes. Doesn't matter why. The length of the payload here is, of course, the same, right, because they're just aliases. So the length of the payload is m-2 to m. You can do the same kind of analysis for the buffer, which is payload length plus 2, right? That's how many bytes we allocate. S to n possibly adds 2 bytes again, doesn't matter. And now we find the mem copy. We have to ask 2 questions. First, do we have enough space in the buffer we're writing to? Right? In this case, yes, we do. Right? So the buffer has at least the size of PL, and we want to write PL many bytes, so that's fine. But we also have to ask, do we have enough data to read from, right? So is the length of the payload at least PL? And here we see, well, it's m-2, but m-2 and PL, they're unrelated. And that's exactly right, because the client could have lied about the declared payload length and the actual payload length. So these 2 things are unrelated, right? And so program analysis can find this kind of bug. And this is a relatively simple analysis. So, I mean, you open the principles of program analysis book, and you will find an interval analysis, and basically you would expect this should not be an issue nowadays. So there's probably a lot of reasons why this kind of analysis was not run in practice. One particular reason that we think was severe is these kind of analyses take quite a bit of time if you do that on a larger code base. So human-computer interaction research says that if you provide feedback and it takes more than 12 seconds, people get frustrated. The software engineering research, they've done user studies where they confirmed that one of the reasons for abandoning static analyses is that the turnaround time of feedback is too slow. So what we're trying to do is we want to do exactly these kind of precise static analysis, but faster. The technique we're going to employ is incrementality. All right. So what does incrementality mean? All right. Let's say we have a larger, source code. This is a made-up graphics, but it doesn't matter. So let's assume this is source code nodes and dependencies between files or something or functions in a project. The idea of incremental analysis is that we only reanalyze things that are actually affected by a change made by the developer. So rather than going through the entire project every time anything was changed, we only want to go through those parts that were actually affected. And from our experience, that's a successful strategy because of two things. First, changes are typically relatively local. It's very rare that the developer makes a change to a project that actually, like a commit to a repository that actually is affecting everything or a large part. Typically, these kind of changes, they're relatively encapsulated into one module or one package or one library or something. That's the first thing. The second is that the effects of these changes, they're typically sparse. So what our experience shows is that when a developer does make a change like this, it doesn't affect everything. It affects things not locally, but in a sparse kind of way. And that's why the strategy of employing incrementality is successful. Because doing this amount of work, tracing where the effect goes, is much more efficient than doing the full reanalysis. All right, so let's take a look at how this might work. So we have the source code on the left, we have the feedback we want to produce on the right. Initially, we have to do a full analysis run. Right? So we haven't seen any of the code before, we just do a full analysis run. It's going to take quite some time. But every change the developer makes from now on will only lead to a small incremental run. Right? So rather than doing the full initial run again and again, we only do this incremental run. And on the right-hand side, you see that instead of computing the feedback from scratch, we are updating the feedback that we had before. So we're invalidating feedback that has become invalid, and we're adding feedback that we can now derive based on that change here. Right? And so for every change that's coming in, we're going to update the feedback again and again. And so theoretically speaking, you can get asymptotic performance improvements by doing that. In practice, we have observed speedups of up to 10,000-fold. Now, the thing is, developing incremental algorithms is really hard, and we don't want to do that from scratch every time again. Right? So every time somebody comes up with a new analysis, you have to develop not only the analysis, but also an incremental implementation of that analysis. That's not how we want to go forward. We are interested in figuring out how do incremental computations work in general. And so we're developing a framework in which people can express computations, and we execute them incrementally for them. And so I'm going to go over the basic ideas of how this looks like before Tamas will take over and show you how this looks like in our tool and do a really nice demo. All right, so our framework has this basic idea that the code, which often you have as an abstract syntax tree, we will represent this instead as a database. It's called a deductive database. Think of Prolog or Datalog. Datalog is actually really close. Then we're going to formulate the analysis as a query against the database. And then we're going to incrementally execute these database queries. And there's a large amount of literature from the database community that helps us figuring out how to incrementalize these queries. All right, so let's look at a simple, really simple code snippet. This is, any imperative language of your choosing. We have some assignments, we have while loop, we have some inline conditional in the last line. As I said, you can represent this as an AST. We represent it as a database instead, as a deductive database. But think relational. So actually, these are kind of relations. So for every kind of node in the AST, we have one relation, which is a set of tuples. A lot of these are actually singleton tuples, which basically just enumerates all the things of that kind. So we have one relation for statements. Every statement in the program has an identifier which occurs in this relation. Right? So in our program we have 5 statements, 1, 2, 3, 4, 5. All of them are statements. But then we have, for every kind of HT node we have this. So we have assignments, and statements 1, 3, 4, and 5 are assignments, so we enumerate them here. We have one while loop, which is statement line 2. Right? So these are all kind of collecting the kind of nodes we have. But then the tree, the AST, also has structure. Right? So we have parent pointers, we have child pointers, we have siblings. And we also encode this as relations. So for example, the next relation says that one node is followed by another node. Right? You can see that. So statement 1 is followed by statement 2. So they are siblings and they are in the next relation. 2 and 3 are not in the next relation because 3 is nested in 2, 3. 3 is nested in 2, statement 2. But 3 is followed by 4 and 4 is followed by 5. That's what we see in this relation. And this way you can represent the entire structure of the program in a relational database. All right, so this is how we represent the data. And then we can write queries against this data. Let's do a very simple example again, before Tamas shows you how to do something more interesting. We're going to do control flow analysis. Control flow analysis computes where the control flows in the program. So for example, we would expect that after executing statement 1, we're definitely going to execute statement 2. So the control flows from 1 to 2. Right? But then with the while loop, we expect that, well, from the head, we go into the while loop, we go through the loop, and then we go back to the head of the loop. That's the kind of control flow graph you would expect. Here in this presentation, we use Datalog rules for explaining how this works. We have 3 alternative rules here to compute control flow graph edges. The first rule says that there is a control flow graph edge from to if these conditions hold. The first is, well, if from is directly followed by to, and from is not some control statement, like if-else statement, but also others. Right? So if from is not special in any way, like an assignment is not special with respect to the control flow, and to is following up on from, then there's a flow from to to. Right? Then we have 2 rules for while loop. So if W is a while statement, and the first child of that while statement is start, then there's a flow from the head of the while loop to the start, to the first child of the loop. And similarly, if last is the last child of a while loop, and W is that while loop, then there's a flow back to the head of the loop. Make sense? All right. So we can use these kind of rules to do our initial run, right? And the initial run is going to start, well, okay, we have this first rule. We have 3 tuples, 3 pairs in the next relation, right? 1, 2, 3, 4, and 4, 5. And neither 1, 3, nor 4 is an if-else statement, so that's why we get these as control flow edges. Then the second rule says, well, okay, statement 2 is a while statement. The first child of that is 3, so we should get an edge 2, 3. And finally, 2 is a while statement. The last child of that is 5, so we should get an edge 5, 2. And that's like how we can do the initial run. We basically try to pattern match these kind of rules against, well, not the program itself, but against the database representation of that program. The cool thing about doing this kind of representation issue and writing those as queries is that we can now actually run this incrementally. So for example, let's assume a developer changes the while loop into an if statement. Right? That's a very small change. So what we're hoping is that the time it takes to update the control flow graph is kind of proportional to the size of the change, and so it should be fast. So in our relational world, in this database world, we represent a change like this as a replacement, where we first delete the old information, then we insert the new information. We don't need to change anything about 3, 4, or 5. They remain untouched. But statement 2 is now no longer a while statement. From now on, it's an if statement. All right, so if we do this, what we basically can do is to incrementally update our old control flow graph. So we can run these rules backwards in a way. So we want to delete while statements. Let's see what kind of control flow edges depended on the information that while statement, that 2 was a while statement. We see that these last two rules here, they have while statement in their body. And so we have to see whether we used one of those rules to derive anything about statement 2. In fact, we did. And that's why we have to delete these two edges from our control flow graph. And I haven't shown the rule for if statements, but they're basically like the first one of while statements. So we're going to reinsert the edge 2, 3, but now for a different reason, because 2 is an if statement. Right? In this way, you can do incremental updates. Well, we can. You write down these rules, we do incremental updates. Okay, this is a really nice small toy example. Under the hood, there's a computational network that propagates all this information, but I don't want to go into detail about this here. And the nice thing is you don't have to go into detail about this either if you're writing analysis in our framework. And that's because of abstraction. So what we provide is we provide relatively normal programming abstractions that you can use for writing static analyses that we will execute incrementally anyways. And you see, for example, for each loop, some pattern matching here, if, else. All of this is going to get compiled into the Datalog rules that we saw on the previous slide, which we can then execute incrementally. At this point, I'd like to hand over to Tamas, who will show you a nice demo about incremental dead code analysis.
All right. So now I'm going to switch over to an IDE. What you see here, this is called MPS, the metaprogramming system from JetBrains. And I'm going to use this IDE to demonstrate how our incremental program analyses are working. And so the first analysis that I will develop is it's going to be targeting the Java programming language. So MPS comes with a Java language implementation. I'm going to use this as my subject language for the analysis. And I already have prepared here a small code snippet. And the analysis I would like to develop is a dead code analysis, but an incremental version of that. So for example, in this program, as I would move around statements, so for example, this is the return statement here, I would expect that I get like error markers, squiggly lines, highlighting different kinds of statements that are now not reachable in the program. I mean, it is obvious that these statements are not reachable because according to how control flows in this method, now I have here this return statement, and so all the rest that comes afterwards, they are now unreachable. And so I would like to now develop this analysis and then hook into MPS's editor infrastructure so that actually it would use the analysis result coming from our analysis framework and then put error markers in the IDE. Okay, so I'm just going to go back to the initial state. And then now I will switch over to what we call an analysis module. So what you see here, this is a domain-specific language that Sebastian was talking about with these abstractions that make it easier to write a program analysis. And so I have already started implementing the control flow analysis for Java. I mean, of course, this is going to be a very simplified version of that. And what you see here, let's just first focus on this function. We call this a function. It's called getFlowTarget. Essentially, the function takes a statement, I call that source, this is the input parameter, and then it returns a statement. Essentially what I would like to do, I use this function to take a control flow predecessor, and I'm interested in what is the control flow successor for that given node. And I already implemented here one alternative, like how we can get one control flow edge. Remember, Sebastian was talking about Datalog rules. This is not Datalog rule anymore because like we are providing these functions, but essentially they are doing the same thing. So we are defining really relations and how we can get edges in the control flow graph. Now, what is written here essentially says that if the source is not an instance of a branching statement, then the control flow successor is going to be simply what is after the source, right? The next statement. This is the straight line control flow case. This is very simple. If you go back to my example here, we also have if statements. So we should also cover if statements, otherwise our control flow analysis will not know like how to deal with the if, and in return our dead code analysis will not know how to deal with the ifs. So what we do here now, I can define alternatives. So essentially, I can define an alternative body for the function, an alternative way of getting an output from the input. And now if we look at the if statement, let me just put this side by side so that I don't need to go back and forth. When we have an if statement, let me just simplify this a bit. So I move this out, delete the else branch. So when we have an if statement, essentially there are many ways how control can flow from here. I mean, we are in a static probe analysis context. We actually, I mean, for simple cases, we would probably know how the condition evaluates, but it could easily be that we read from some user input and then we don't know that. So considering this, the control could flow from the condition of the if statement into the then branch, right? Then from the then branch, I mean, assuming that this would not be a return statement, if we are at the last statement in the then branch, then the control could flow to the statement that is after the if statement. And also a third alternative is that considering that the condition evaluates to false, the control can flow from this condition to the statement that is after the if statement. So these are the three cases. And now these are the three cases that I also would like to encode in this analysis DSL. So let's start with the first case, which is saying that the source statement, which we have at hand, is an if statement. And then one alternative for getting an output is simply the next statement after the if statement. Now, yet another alternative would be that we have an if statement at hand, and then we can query what is the first statement in the then branch of that if statement. So now what I could say, I already prepared some helper functions here that I'm going to reuse. So I could call get first statement, and then I pass in their source. So now I know that source at this point is an if statement. I had here this constraint, and I'm querying what is the first statement in that if statement. And this will return for me this guy here. Now I need a third alternative. That is the most complicated one, because essentially in that case, that would be the alternative where source is the last statement in the if, and I want to go to the statement that is after the if. What I say there is that I need to query what is the container if. Like this is the containing if statement. So I already have a helper function for that. I can get the container if statement from source. Then I want to ensure that actually this source is the last statement in that if statement. And then if that is the case, then I want to return the container if's next statement. Right? This way I can simply continue with the statement that is after. So these are all the alternatives. I mean, if you would like to, you could just simply create a new function and then pack these alternatives in there. So we could do that. I create a new function. This is going to be the control flow that is handling the if statement related alternatives. So I could create this statement. It returns a statement. And then I will just take these alternatives and then simply copy them over here. So this way I get rid of this here. And then here I return the cflow if, passing their source. So the nice way about doing this is that there are many alternatives that we are not handling here. Different kinds of branching statements, while loops, do while loops, and so on. So you could just simply have a function that is handling that case, and then you could just use that here in this flow target function, which is kind of like the main function. Now, there is also something here. This is a relation. So as an analysis developer in our DSL, you have the option to either define functions, if you like that, or you can also just resort to writing relations. And notice here that the relation here doesn't have like output parameters, so they're kind of like, it doesn't matter here that what is the direction of the parameter. So it's up to you as an analysis developer what makes sense. I implemented here a relation which enumerates for me a binary relationship. It says what is the transitive reachability in the control flow graph. So given a source statement, I want to transitively get the target statements that are reachable from that. And this will be important because I want to use this in the dat code analysis. Notice here that this here actually is using the function that I defined above here, this one. And also there is this plus symbol, which is our framework has built-in support for incremental transitive closure. And so this is what this one stands for. Okay, now the next piece, I mean, I already have the control flow analysis, would be to develop the dat code analysis. So I'm going to create here a new analysis module. And I'm going to call this dat code. And I would like to essentially have a unary relation which enumerates for me statements that are dead. They are not reachable, essentially. So the way how I will do that, I create here a relation. I'm going to call this unreachable statement. It has one parameter. So this will be of statement type. And then now, the reasoning that I would like to follow is that I would like to get the container method for this statement. I would like to get the first statement in that method. And then I would like to ask the question if this statement is reachable from that first statement or not. because if it's not reachable, then we have a problem. So I'm going to create a local variable method. I'm going to get the container method. I already have a helper function for that, but I need to import the common module. So get container method. I pass in their statement. Then I would like to get the first statement in that method. So I'm going to use the first statement helper function, and I pass in their method body. Then I would like to say, with an undef construct, this stands for negation. I would like to import my control flow module, and then say that remember now I have this relation, the transitive reachability, that first is actually, so statement is not reachable from first. This is how I formulate it. I use the undef construct, which stands for the negation. There is one more thing here. This is like a small detail. I also want to rule out the case where first is the same as statement. So this is just to rule out the first statement. Okay, so now we have essentially almost everything implemented. Now we just need to hook in the IDE editor infrastructure to actually place an error marker. So for that, I'm going to create here what is called a checking rule in MPS. So I just give this a name. This will be called check that code. This checking rule is triggered for statements. I'm just going to give this a name. And so what I would like to do here, I would like to query this incremental evaluator to tell me the analysis result, because now if this given statement for which the checking rule is running is considered not reachable, then I would like to put an error marker. So we actually have a DSL to access the analysis result, so that's what I'm going to use here. I would like to get an evaluator for the unreachable statement relation. This here is just a small detail. I need to specify a scope for the evaluation. Doesn't really matter for now. So I'm just going to call it the evaluator. Then I construct a new tuple, the tuple in a relation, where I say that, let me rename this to candidate so that it's visible like what I'm doing here. So I'm creating a new tuple in this unreachable statement relation. I'm just going to call this T. But I would like to ask from the system, count me the number of tuples. Actually count me this tuple, like how many times this is present in the corresponding relation. If this is greater than 0, then we have a problem, because then we have an unreachable statement. So let me put this condition here into an if statement. So if this is true, then I would like to put an error saying that this is unreachable, and I would like to highlight the candidate function. So now I build all of this infrastructure, I build the analysis. Essentially, building the analysis means that I'm generating this computation network, which Sebastian didn't want to talk about. When I'm building this checking rule, then respective functionality is generated so that we can hook into the editor mechanism. And so now we can go back to our example code here, the dat code, and then play around with that a little bit. So at this point, we are not expecting any kind of error marker, because we do not have dat code in this program. But then, for example, when I move the return statement now one level higher up, then we have a problem. Immediately, all of these statements are now underlined, saying unreachable, potentially unreachable code. Also, I mean, I can immediately play around this, move the statement up and down, and you see that immediately all the other statements are now highlighted. So essentially, what you see here, as the developer modifies the program, immediately feedback is provided about which parts of the program are not reachable anymore. So for example, if I move the return statement back to the then branch of the if, then all of the errors go away. So with that in mind, I would like to give back to the presentation to Sebastian, and then he will also talk about more sophisticated data flow analysis.
Presentation. All right, awesome. So that was a demo of incremental dat code analysis, which is, it's not a simple analysis, but in some way it's relatively simple. So we have evaluated this in our research papers, where our goal has always been that we want to be able to use this framework to give feedback to developers as they type, right? So not at commit time or something like this, but really as they type. So our goal was to give feedback within 100 milliseconds. And with what Tamas showed so far, we did two kind of case studies. We did a find bugs analysis case study, so finding simple syntactic patterns in source code. If a void method in Java has a return statement, then that yields a warning, some things like that. And we get really fast update times there. And then we did control flow analysis, so that's similar to what Thomas just showed you for C and for Java, where as you change the program, you get updates to the code analysis and the control flow analysis underlying it in less than 30 milliseconds on average. So that's great because that's really like interactive feedback provided to the developer. You see there's some gaps on this slide. We will fill them in a little while. And the reason there's gaps is because they're two kind of, we distinguish two categories of analyses. What we've discussed so far are really analyses that are using the power set lattice. Right? So power set lattice is just a set of elements. Right? So that's exactly what we've been modeling so far. So relations, right, that collect tuples. And that's quite expressive. You can do a lot of things with that. You can do complex expression elimination, simple points to analysis, simple uninitialized read, simple dead code analysis. All of these you can represent, you can encode them as relations. On the other hand, if you think back of the heartbleed bug example we discussed at the beginning, where we needed an interval analysis to do the bounce checking, well, it's not so clear how to encode that as a relation. Of course, you can enumerate all the numbers in some interval, but that's not going to yield an efficient checker. So on the other side, we have analyses that are using what we call custom lattices. Really what we mean is anything but the power set lattice. Right? The power set lattice one-to-one corresponds to the relations that we can incrementally maintain. All the other lattices do not. Right? So here we have, if you want to analyze numeric operations, then you want something like intervals, right? And that's a custom lattice. If you want to analyze string operations to do, for example, SQL string injection detection, where you want to reason about patterns of strings that are being composed at runtime, you want to analyze that statically, you need some lattice over string patterns. If you do type checking, you need some lattice over types. And so there's still relations under the hood, right? The control flow graph is still a relation. But also there's new challenges. We need to be able to generate lattice values, and we need to be able, and that's really the hard part, we need to be able to aggregate them. So for example, for the interval, right, if you have a while loop, and in each iteration you do +1 to some variable, you're going to make the interval wider and wider, and that's an aggregation operation. So again, like before, I don't want to talk about the technical details of how the backend works. I'd rather give you the high-level idea, and then we're going to move back to a demo and show you how that works in our framework. So let's do a very simple example where we need aggregation. That's not an analysis example. That's just a list of numbers where we want to find the maximum. Right? So what you can do is you can just scan through the list and find the maximum. Right? And as you do that, well, you move to the right and you found, okay, 7 was the maximum. The problem with this approach of computing the maximum is that what happens if you delete 7? How can you, with what you have done, find the new maximum with minimal effort? Well, if you do a linear scan through the list, that's not going to be easy. So what we typically do is we reorganize the computation such that these kind of updates become more efficiently handleable. All right, so the typical solution, that's not something we've made up, and we're just using this approach as well, is to do this kind of computation in tree-based fashion. Right, so you can compute the max between these two numbers, you can compute the max between these two numbers, and then you can compute the max of the two resulting results. Right? In this way, you get like this tree-shaped computation of an aggregation operation. And that works whenever you have an associative operation, like max here. And so now if we delete 7 again, all we have to do is we have to reconsider the path from the change to the root. Right? And so, well, we've deleted 7, so the max from 1 and 7 now cannot be 7 anymore, it's really 1. And so we're updating that to 1, and that propagates upwards, and now we get a new max, and we've only required log n many computation steps rather than scanning through the full list again. So now the nice thing is, you can do the same for lattice operations, which we need in static analysis. In static analysis, what you need to do is you need to join
two lattice results or you need to meet two lattice results. And these join and meet operations, they're associative. So we can represent this as a tree, just like we did for the max function, and then we can compute the least upper bound over an entire list of data, right? And so our strategy from a high-level point of view is, well, first we collect all the aggregates that are going to be combined in a list, well, in a bag. And we already know how to do that incrementally, right? That's just a set. Right? So we're going, for this while loop example, we're going to collect all the small intervals that you want to join. Then we do this tree-based aggregation. And now, maybe you've noticed, right, I deleted the 7 in the previous example. Well, if I do that often not enough, the tree is going to degenerate into something that doesn't give you good performance. So we also rebalance that tree. So we actually use an ABL tree implementation under the hood. And so this is our high-level strategy for how to handle aggregations. And that becomes really important in doing static analysis. There's some more technical challenges that we will talk about later. But again, the nice thing is in our framework, we can provide abstractions that hide from a lot of that complexity. Okay, so we have some way of declaring lattices, and we have some way of saying that you want to do aggregation, but you don't have to reason about this tree shape, this rebalancing. Actually, not even that you collect and then aggregate. All of that is happening under the hood. And so let me hand back to Tamas, who will show you how you can use this approach to do an incremental array bounds check in IncA.
Okay, so this is the same story as before. I'm going to switch over back to MPS again. I prepared here some simple subject program that I would like to reason about. This is going to be an array bounds checking. So I have defined here an array of size 10. Then I'm doing some random initialization. And then I have some dummy code initializing some index variable. And then I have here two reads from the array. Essentially, I'm accessing an element at the index position. So obviously, at this point, I would need to know like what can be the potential value of index in order to reason about whether this is an out-of-bounds access or not. And there's also like this kind of access where I'm just simply using an integer constant. And so for example, if I would put here 10, that would of course be a problem. So I would like to see here an error marker complaining about this. Or also if I'm using here a negative number, that's a problem. And so again, these are the kind of things that I would like to now provide feedback to the developer so that as the code gets changed, these error markers are immediately updated. Okay, so as a preparation for this analysis, I have already implemented an interval analysis. So I'm not going to go into a lot of details about that. Instead, kind of like just provide a sneak preview. Essentially, we have a DSL for the definition of lattices in our framework. And this is here the interval lattice. I implemented all the lattice-specific operations. There's less or equal, the partial order. There's least upper bound, greatest lower bound. I also have here helper functions that are interpreting different kinds of binary expressions like plus, minus, and so on in the interval domain. So this is important because as you're doing operations in the program and you want to reason about that statically, we need to know like what does it mean to perform a multiplication in the interval domain. I also have here helper functions like if two intervals are intersecting or not. And this will become interesting when I actually implement the bounds checking because then I want to see, for example, if the specific index is in a negative range or not. Then I have here the actual interval analysis implementation that uses the lattice that you have seen before. So again, you don't need to read this code. It's a lot of code. The important detail is that this interval analysis is flow sensitive, so it knows how the control flows in the program. This is the same control flow analysis that I implemented in the previous demo, so that's something that I reuse. And so maybe let's just look at this get interval before function, actually just the signature of that, so what this really does. It takes a node, which is a statement, so this is a control flow location. It takes a variable, and then it returns an interval lattice value. So essentially what this means, I can ask this function, okay, what is the interval associated to the variable at a specific control flow location? The tiny detail, you can see here an annotation on this return type. This is actually super important. This is doing the aggregation. So with this, I'm instructing the system that when there is a control flow merge point in the program, then it should use the least upper bound operator to aggregate interval values together. And now the nice thing is that, your job as an analysis developer is to place this annotation here. Our job as the framework implementers is to actually incrementalize this computation. You don't need to care about this. Okay, so let's get started. I'm going to create a new analysis module, and I'm going to call this bounds checking. And I'm going to take this small code snippet here, put it side by side, and we should reason a little bit about what we actually want to do. So given something like this, which actually I can peek behind it, what is the even, with respect to my language implementation, what is the concept behind it? Well, it's called an array access expression. So I need to focus on array access expressions in my analysis implementation. And if you look at this, for now I'm just going to assume that on the left-hand side we're always referencing a variable, just for the sake of this example. So, okay, we have an array type variable, which is actually pointing there. Then an array type variable has an initializer, so somehow I want to extract what is the size of the array, in this case 10, because I will need this value to reason about if we have an out-of-bounds access. And then another thing is I need to get this index, which is in here between the square brackets, because then I want to compare against that. So let me define here, again, a relation. So this is going to be a unary relation, and I'm going to call this the erroneous access. And this has one parameter, so I'm going to call that access, and its type is array access expression, as you would have expected. Then, from this array access expression, well, it has, first of all, an array part, which is this guy on the left-hand side. It has an index part, which is this guy on the right-hand side. So I need those. So first of all, I'm going to get the array part. So I say the array. Again, for the sake of this example, I assume that this is a variable reference. I want to actually formulate a constraint against that. So this actually holds. So I say that this should be a variable reference. Then, because this is a variable reference, I can actually get now the referred variable. Right? So at this point, we are here at this array, type the variable called R. Then from that, I would like to get the initializer expression. Right? So I say variable.initializer. Right? Then let's take a look here. Well, I'm interested in what is called a generic new expression. So I formulate a constraint. I'm only interested in the generic new expression, right? Now, a generic new expression has this inner part, which is called an array creator. So I'm interested in that. So from the init, I'm getting the creator. Then I say that it should be of type array creator with an instance of. And now from there, the array creator has a dimension. I need to query that. So I'm going to call that size. And that's going to be the creator.dimension expression. It doesn't really matter why I need to do all these traversals. I know how the language is implemented. It's just simply I need to traverse along these edges in the AST. Okay, so now we have the size. But the problem is that this size is currently still a program element. I need to somehow turn to the interval domain, right? Because I will then do the checking in the interval domain. So what I want to do now, considering that this size could actually be here some other value, I actually want to reuse my interval analysis and then simply ask the question, so I create a new variable here, size interval. I would like to ask the interval analysis, hey, tell me what is the interval for this given expression, which is size here. So if we look here in the interval expression, which I implemented before, we need a control flow location. Now we need to get that control flow location. So that control flow location is going to be the container statement of that expression. So I already have a helper function for that. So container statement, and I simply pass in there our reference. Now I have everything. So I have the statement, I have the size, and now at this point, if I ask the type system, okay, what is the type of this size ID? It tells me that it's an interval lattice value. So we are good. We are in the interval domain with the size. Now we need to do the same thing with the index. Right? So what I will do now, I have this array access. So now I want to get the index. Right? So this is going to be access with index. Again, I need to turn this into the interval domain. So I'm going to create a new local variable for that, size ID. And again, I'm asking the interval analysis to tell me what is the value, like what is the interval at that point. And so I'm passing there the statement and the index, and now we are good. So now we have this value here represented in the interval domain, and we have this value represented in the interval domain.
For the get interval expression, well, the first one you want to use var, like the statement of the declaration. The other
No,
one, the other one, size ID.
No.
It's the initializer. It's the
This
expression of the.
I'm pretty sure no.
Okay.
Okay.
It's probably right.
So I mean, here, this size. This is what you
No,
mean.
the statement in that line should be var. Like you want this, you want the size of the expression in the statement where you declare the dimension.
I see. Okay. Well, yeah, we can do that. So this one here, right?
Yeah.
Okay. Well, but then this is a problem because I would like to ask the question like I'm
that's
at
from the
this
ref.
point.
These are different statements.
Yeah. Okay, we can do that. So let's say that this is the var container, and so then I could just simply copy this, and then this would be the access container. And I could use that here. Okay. Now, the important piece would be that we actually make use of these intervals. And for that, I'm going to simply I'm going to formulate a constraint. And I will resort to Java code here. I would like to do this comparison in Java code. And so this is just simply an implementation data that I create here a closure. And so what I would like to say here, there are two cases. Either we have a negative range. So I'm going to formulate that by saying the interval lattice, I already have helper functions implemented there, the is intersecting. So I want to ask the question whether the index interval is intersecting with the negative interval, because that's a problem. So I'm going to pass in there the index ID. So this is an interval. And then I would like to say, essentially create an interval range by myself. So for the lower bound, for the sake of this example, it doesn't really matter. I could just say integer min value and -1. This is the negative range. We are talking about integer ranges here. So this is one of the cases. So if this is true, then we have a problem because then index is in a negative range. So this is going to be one condition for being an erroneous array access. But then we have another case, that is the more complicated one. I need to get the size interval. From that I need to get the lower bound, and then I want to ask the question if my index is higher than that, because then we have an out-of-bounds access again. So I take the helper function for querying the lower bound. I pass in there the size interval. So I'm going to call this the low value, and then I copy this statement here, formulating the second condition. And then I want to say if the index interval is intersecting with an interval where the lower bound is this low value, and the upper bound could be just integer max value. Doesn't matter for now. So this is the other alternative. So if any of these conditions hold, then we have a problem. Now, again, I need to hook into the editor functionality, creating the checking rule. So I'm going to call this check access. And I'm going to just copy some code from here, from before, from that code analysis. Again, the thing that I would like to check is an array access expression. I'm just going to call this X. And so here I'm interested in the erroneous access relation. Just fixing the code here. And then I have, essentially I would like to ask the question from the engine if the tuple where the access is this expression that comes in here, this guy is actually in the relation or not. Because if that is the case, then I would like to put an arrow marker on the expression saying that this is a potential out of bounds access here. So now again, I'm building the analysis infrastructure and the editor infrastructure, and hopefully our analysis will say something. So going back here to the array access. Okay, Okay, so probably I have messed up something because you should see some errors. Yeah, let me go back here, the bounce checking. Yeah, I'm wondering if I messed up here something with the interval expression. Yeah, for the
Is var a statement? A variable definition?
No, that's not a statement. This is just, sorry. I think it's just a variable reference. So let me just simplify this a little bit. So we need the container statement, that's for sure. So I think initially I had something like this for the size, and
Just try it.
yeah, yeah, I'm not sure. I don't want to spend too much time on this. What I could do, I could just simply go and check out the head version of the repository because I actually prepared this analysis. So let me just do that actually, so that this demo is not going into waste. So let me rebuild now. I have here the implementation. So essentially, you see here now the error that I was talking about. This is a potential out-of-bounds access. And so if we play around here with this code, like I change here this 2, then the error goes away. Also, if I do here the change, like I say 10, then we get the error. And so these are the kind of the problems that we would like to notify the developer about. Yeah, so this was the interval analysis example and the array bounds checking.
Awesome. Okay, so we do need lattices. We need lattice aggregations, right? So we can compute about these intervals. We can reason about whether things are intersecting or not. And so the computational networks that we get for analyses that are serious, they can be rather big. Oh, wait, that's not it. Okay, so this is an analysis we're currently working on. It's an inter-procedural points to analysis for Java, where everything that has a single color is mutually dependent computation nodes, and everything else is you can run in parallel, or well, not in parallel, but is independent from one another. And so these computation networks, they become really big when you do real-world analyses. So the question, of course, is what does that mean for our goal of providing feedback within 100 milliseconds? And so we've done some evaluation. This is not the computation graph from the previous slide. This is inter-procedural analysis. We have a strong points to analysis, a strong points to analysis on 4 code bases, and we have a string analysis to reason about patterns of strings that are being produced at runtime. And these are all on Java. So what we've compared here is the initial runtime of running our analysis. And that's in the ballpark, it's a log scale. So 6 seconds to 64 seconds for the largest code base, which is about 70,000 lines of code, I think. For the strings, it's like 20 seconds initial runtime. And you remember, right, our goal was 100 milliseconds per edit operation that the developer does. And we actually managed to achieve this. So even though these analyses with lattices and recursive lattice aggregations become really complex really quick, the time it takes to provide an update on the feedback seems to kind of remain stable, which is great news for us. Right? So we get like 6 milliseconds, 10 milliseconds, really fast feedback times. So if we come back to this slide, so now we can start filling these gaps. All right, so we've talked about data flow analysis, which is a paper that Thomas is going to present on Thursday, where we managed to keep the update times down to 10 milliseconds. We also have, and we're still exploring, how we can use this framework to do type checking. We explore a little bit on Java, we're exploring on Rust. A student of ours has actually implemented a large part of the Rust language, or type checking for a large part of the Rust language, and got some promising results there as well. So
To conclude, let us emphasize that all of this is open source code. You can find it on GitHub under this address. There's quite a few challenges that we're looking forward to working on. We are always in need for help, so if any of this is interesting to you, come talk to us. One of the things we really want to do is we want to take this project and make it available outside of MPS. MPS is the IDE that Tamas has been using, and integrate into other editors as well. We want to optimize memory consumption. We want to be even faster, do dynamic optimization based on how frequently a part of the code is actually changing, because if something is not changing a lot, you don't need to cache it so much, right? Because a cache miss is just less likely to happen. And so there's a lot of ideas for how to improve this framework even more, besides, of course, making it more expressive and covering more static analyses. And so if you're interested in how the backend of IncA works, there's going to be a talk on Thursday at Uppsala that Tamas is giving, and you're warmly welcome to join us there. So this is it for today. Thank you very much for your attention. If you have any questions, I propose we don't do a question session, but we just stick around and you come up front and we discuss if you would like. Thank you very much.